Hello everyone. So today we are going to learn about strain energy. So strain energy in our syllabus, which is Cambridge 9702, is defined as the elastic potential energy, which can be regarded as strain energy, to bring a change or deform a shape of a material. Now, strain energy can be easily found out from the graph that's given to us as force and extension graph. So let's see, this is force and this is extension. Now if you plot the graph like that, so we must understand that at limit proportionality the graph stops following Hooke's law and starts to curve. Now at this particular point, before this, if we find out the area under the graph, what I mean by that is that this area, this whole area is the elastic potential energy or the strain energy, and since it's actually equal to the area under the graph, so it seems like a triangle, so we could use half times base into height, that's the area for the triangle, and here the base is x and the height is f. This is the base x, and till this point this whole is f. Alright, so we could say half fx is equal to elastic potential energy. Now we can also change it according to our needs and whatever the question demands, and that is, since we know that f is actually equal to kx, so we can just put this kx right here, right? We can just substitute it, and then we get kx times x, so it becomes half kx squared. So this is one more formula that will be quite handy. Alright, now there are a couple of questions that comes in your paper 2 and paper 1 that we need to focus, and there's some I took out. There's one question or two I think I took out, so let's solve them and see if you understand the idea. Alright, so I took this question out, which basically says that there is a moving car at a velocity of v, which is going to hit the slider, and the spring is going to compress. Now they have given the variation of compression x, and with this force exerted on the spring f, right? Now first thing, whenever you look at any diagram, especially graphs in CAIE, always try to see the axes and the units. So here in the y-axis, alright, the force is given in newtons, and here on the x-axis the extension or the compression is given as x in centimeters. Alright, so this is a straight line, but one thing I would like you to focus, and that is, if you look at here, the graph does not start from the origin. Now this is one trick that usually CIE people do, and you must understand that the force extension cannot be made if the force is zero. So basically, extension will always be there if there's a force, so which means the graph has to start from an origin of 0 and 0, right? Now here they are actually showing you false origin, so always check in such questions, check for units and x's, and then check for false origin. If there is a false origin, which means the graph is not given from here, in fact the graph was plotted from somewhere here, which means if we try to find out the area under the graph, which is like that, this will be wrong, since area under the graph would be this whole thing. Alright, so let's see what he is saying. Now in the first part he says figure 4.2 shows compression for f 1.5 to f 4.5. The car comes to rest when f is this. Use the figure to show that the compression of the spring obeys Hooke's law. Alright, now as you remember from the last video, the Hooke's law means that the force should be directly proportional to the extension, provided that limit of proportionality has not reached, which means that in this the graph is a straight line. Alright, oops, hold on. Alright, it's a straight line, so it means it shows that you can obviously write it in your words, but straight line, which means the graph or the material, whatever it is, in this case the spring, follows Hooke's law. Now then you have to define what is the Hooke's law. So you could say that the force and the extension are directly proportional. That's why. Alright, and limit of proportionality is not raised. So that's why you're going to score 2 marks. Now then it says determine the spring constant, and like in the previous video I told you that the spring constant K is defined as the change in force over change in x. Now let's see. So I'd rather take because I know that this graph has to start from 0, so instead of taking this point, I can take this point for sure, but to actually make my life easier, I would rather avoid it. I'll take first point as 0 and 0, that's origin, also the line start from, and the second point as this, so it's 4.5, and you can take actually any point on the graph, it doesn't matter. So here, now it's basically on the x-axis, it's basically let me check how many, what is the one box counts for. So if I could always do that by using simple mathematics, and this is like there are 10 boxes from in a change of 0.1.5. so basically if I change it, so 0.5 is actually divided, that's the change, right? That's the change. So the change is divided in 10 boxes, so each box is going to be 0.05. Now I know that here it's the middle, so it's 1.75, I think, yeah, and plus one box which is 0.05, so it's 1.80. okay, now so I'm going to write it as 1.8 and 4.5, that's my point here. Now if I try this, so let's see what is the change in x and change in f. So the change in f is basically 4.5 newtons minus 0 divided by 1.8 centimeter minus 0. Now one thing I'd want you to note is that since in the answer they've asked for you to find Newton per meter, and the x-axis obviously was given in centimeters, so you have to change it either before putting in this formula or afterwards, after you find the answer to this. Alright, so if I try to find the answer to this, let me just quickly open the calculator. So it should be 4.5 divided by 1.8. So my answer is 2.5 newtons per centimeter. Alright, to change the centimeter, I have to divide the centimeter with 100, which will multiply there. So actually, this is going to be 2.5 times 100, which is exactly equal as 250 Newton per meter. Now, you might be wondering how I have actually multiplied 100, because you see, it's quite simple, that you should always write it as this and then change it. So if I change it, so it's going to be 1 over 100 meters. Alright, so it's double dividing, so the 100 would multiply there. That's how I got the answer. That's 250 Newton meter. Okay, now it says determine the elastic potential energy stored in the spring due to card being brought to rest. Now, a lot of people might use this formula and this half into F into X. Now the problem with this formula is that it will give you, it will require you to find the values, right? So a lot of people, what you need to understand is that they might take the value from here till here, which is actually a change in F, that's I think 3, which is wrong, because I told you it should start from 0. So on the height, on this height, the force should be actually 4.5 and the length should be actually 1.8, or rather, if you divide by 100 right now, so it's 0.018 meters. Now, what most of the people do is they take this change, and that's actually wrong, because your reading should start from 0. That you need to emphasize. That's why they have given you the false origin. Now if you're using this formula, so from this formula you can get like add 4.5 here and then 0.018, or I would suggest taking this formula, that's half kx squared. So it's half, you found out 250, in case you couldn't find out, so you could use that, and then for x we can multiply 0.018 whole square. Now if I solve this, so it's going to be a half times 250 times 0.018 power 2. Okay, so the answer is 0.041, correct to two significant figures. Alright, so I've done it and it's in joules. Now you see they are requiring you to find something in joules, and so joules is the SI unit. So anything that's given as SI unit, you have to convert it. If I had used 1.8 here, which is centimeters, centimeter is not an SI unit, which means that the joules would not come, because joules has to be in all the SI units, so be careful about that. And even if you use this, so let me check if it's the same answer. So yep, it's also 0.0, it's actually 0.0405, but since all our readings are correct to two significant figures, so it's best to write it as two significant figures. Alright. Now, in the next question, he says that calculate the speed v of the car as it makes contact with the slider. Assume that all kinetic energy of the car is converted to elastic potential energy. Alright, so it means when the spring was like fully compressed, so the energy, the EPE, was actually 0.041. So the car initially, when it was not compressed, the car hit it with the velocity v. So if there's an exchange of energy between kinetic to potential, and we understand there's no loss, which they're saying. So we could say that kinetic energy should be equal to the potential energy. Now, it should be half mv square, and the energy that we have calculated is 0.041. I believe the mass of the car might be given somewhere. I skipped it. Okay. Yeah, here. So the mass is given as 1.7 kg. So yeah, life becomes easier. Okay. So from here, let me change the pen because just make this little contrast. So we could say V square is equal to 0.041 times 2, the 2 multiplies here, and divided by with the mass, that's 1.7. And if we take under root on both sides, so we can find V. So let's see what might be the answer. Alright. Okay, so under root and 0.041 times 2 divided by 1.7. Okay, so the speed has to be 0.22 meters per second. So that should be the speed. Now, although the other parts were rather simple, but the only thing that I wanted to tell you was that always check for false origin and the unit in axis. And this is one part where most of the students, although they have all the concept, they do the question right, the values are right, but since the units they take wrong, so in the end they end up with really bad results. Alright, so I hope you like the video. You can subscribe and share the video, and good luck.